Today we're going to introduce the basic concepts that surround the ideas of work, power, and energy. We're going to leave the relationships between these concepts for another day, but I just want to introduce the terms, the terminology, what affects each type of quantity, and get those terms and ideas out there for you. So let's start with the idea of work. And a lot of these terms are not really defined by much other than their mathematical characteristics. So work is the product of force and displacement. So it's relatively straightforward, as are many of the terms that we're going to talk about here today. Work is the product of force times displacement. So W is equal to F times X. Now, it's actually a little bit more complicated than that, because only forces that are parallel to displacement can actually do work on an object. So technically, this W equals F times X. Well, it's really the force parallel to the direction of motion or your displacement. So if I take this bucket of balls here, if I push the bucket across with my hand being horizontal, you can see this part of my hand is horizontal, I'm exerting a force that's in the direction or the plane of motion. So that force can do work on the object. It's a force and a displacement. However, if I take this thing and I pull it like this, you can see that my arm is at an angle. So I'm exerting a force at a particular angle. Well, only the component of that particular force is going to do any work. So in the first situation, I had my bucket and I exerted a force horizontal. So the entire force does work. However, if I'm pulling that bucket at an angle, so here's my bucket, and now I exert a force, it is only the X component of that force that does any work. So in this regards, W equals the full force times the displacement. So if I push with a force of 10 newtons for a distance of 2 meters, I'd put 10 newtons in here. I'd put 2 newtons or 2 meters in here, and I'd come out with 20 joules, because our unit for work is the joule, and a joule has a symbol of a J, and it's equal to a newton times a meter. However, if I pull this thing across the table, and I'm now exerting a force that's across and up, then only this X portion. So work here is equal to the X component of the force times X. So if this force here is 10 newtons, just like this force is 10 newtons, we're actually going to do less work over here because F sub X is less than F. So it seems super simple, and for the most part it is. Work is the product of force times distance. There's a few circumstances where we got to get specific and make sure we understand that only forces parallel to the direction of motion actually do any work. Here's one of them. Circular motion is another one. So if I take this ball and I twirl it around a vertical circle, or any circle for that matter, and we talk about the forces acting on the ball, and we talk about the tension in the string here. If I pause this thing right here, then the tension is pulling this thing in that direction. But if you remember anything about our circular motion, the direction of motion is always tangent to the circle. So if I pause this thing here, we're pulling this way, yet the direction of motion is upwards. So if I were to draw a situation here for circular motion, let me get rid of all this stuff here just to make it a little bit easier. If I were to draw a picture of what's happening here for this circular motion, when the ball reaches here, it wants to go straight, V. So my displacement is being directed upwards because that's the direction of my velocity. Yet the tension in the string right here, F sub t, must act towards the center of the circle. That's a condition of circular motion. Well, there is no portion of this thing that's in the direction of this. So when I just did the bucket and I moved the bucket at an angle, my force wasn't in the direction of motion, but a portion of my force was. Here, my motion is vertical and my force is horizontal. I can't get a portion of this force that's in this direction. So since this tension force is perpendicular to that velocity vector, work must equal 0 because there's no force parallel to this, no force or portion of the force parallel to this displacement that can do any work. So for circular motion, the work done is always equal to 0. The work done for the object or for the force keeping the object in the circle, at least. What about if I push on the wall? If I push on the wall, I'm going to get really, really, really tired. I might start sweating. My shoulders are going to get sore, but I could push on that wall all day long and I'm never going to do any work. How come? Well, because work requires displacement, and displacement requires moving an object. If I'm pushing the wall, my X value is always going to be 0. So I'm never actually going to move the wall. So therefore, I'm going to exert a lot of force, but I'm never going to move the wall. So my work done is 0 unless there's actually displacement of the object. Let's put a little math to this. So we've got 2 examples here. In each of the following situations, how much work is done if Joe pulls a 10-kilogram wagon with a force of 30 newtons so that the wagon moves 20 meters? Well, let's take a look at our 2 situations. Joe weighs 300 newtons and pulls the wagon so that the handle is parallel to the ground. So here's the wagon. Here's Joe. Joe is exerting a force on the wagon that is parallel to the ground. Well, the wagon is going to move along the ground. So in this particular situation, this entire force is causing this wagon to move. Well, work equals F times X, or F times delta X. Remember, only forces parallel to the direction of motion can do work. But Joe's force of 30 newtons, look at Joe weighs 300 newtons. Well, that's irrelevant. How heavy Joe is doesn't matter. Joe could be 700 newtons, 300 newtons. Some big people pull not very hard. Some small people pull super hard. It's not about how big the object is that's causing the force. It's how big is the force. So that entire 30 newtons is helping to move the wagon 20 meters. So work is going to be equal to 30 newtons times 20 meters, or 600 newtons times meters, or 600 joules. But if Joe pulls this wagon so that the handle makes a 50-degree angle with the ground, his entire force of 30 newtons isn't going to do any work. Only the X component of this thing is going to do any work. Why? Because the force is not in the direction of motion. You pull the wagon along the ground. So therefore, only stuff that's horizontal to the ground is going to do any work. Only forces that are horizontal to the ground. Oh, my bad. I even got messed up. It's 50 degrees outside, but the handle makes a 40-degree angle with the ground. Certainly the temperature outside doesn't matter. So now W equals F parallel times X. Well, what's F parallel? That's this X component right here. So that's going to be the full force times the cosine of the angle times X. So that's going to equal 30 newtons times the cosine of 40 degrees times a distance of 20 meters. And you can see that this is going to be someplace less than 600 joules because the cosine of 40 degrees has to be less than 1. Only forces parallel to the direction of motion do work. Now, what if we graphed force versus displacement? Let's talk about our graph of force versus displacement. Now, we had one of these graphs on one of the labs that we did. If we're going to talk about graphing force versus displacement, and in our case, it'd be fair to say that these are forces that are doing work. If I were to graph force versus displacement, let's say, again, Joe had a constant force of 30 newtons. This is another example of where graphs tell stories. The fact that this line is straight across means that that force is a constant force. One of the things when we talk about graphs that tells us information is the area under the curve. If you're doing calculus, it's the integral. But if you're not doing calculus, you just focus on the idea of area under the curve. Well, the area under the curve of a force versus displacement graph will always give us work. So the area under the curve for force versus displacement graph is work. Look at it. This doesn't come out of nowhere. It comes because of the equation that represents the idea of what work is. Work is the product of force and displacement. Well, force is on the y-axis, x is on the x-axis. Therefore, the area under the curve is going to equal my work. Now, what the graph look like for our spring lab? Maybe the graph could look like this, which is kind of what our spring lab just looked like. But no matter what, no matter where you get this graph from, obviously then our shape here is a triangle and our area is 1/2 base times height. Whereas before, the area was a rectangle and the work done then would have simply been base times height, or the area of our rectangle. So there's the idea of work, relatively straightforward. Real idea for this unit that we're going to explore in future lessons is the relationship between work and energy. But let's first talk about what energy is. Well, energy is the ability to do work or the ability to change an object or its environment. There are lots of different types of energy. Nuclear, thermal, solar, tons of different types of energy. In our course, we focus on the idea of what's called mechanical energy. And mechanical energy is the sum total of gravitational and potential, of kinetic and potential energies. Kinetic energy is energy of motion, and potential energy is energy of position. And mechanical energy is the sum of kinetic plus potential. So mechanical energy, and I'm going to say ME is mechanical energy, is the sum total of kinetic energy plus potential energy. Now, these are terms that you might have heard in 5th grade, in 7th grade, in 8th grade. So we're going to run through them pretty quick. Remember, our real key here is how do all these terms link together? Today, we're just introducing these terms. Kinetic energy is energy of motion. Well, what types of objects have, excuse me, a lot of kinetic energy? Well, if I take this golf ball, where's my golf ball? If I take this golf ball, I could give the golf ball some kinetic energy. How do I give the golf ball kinetic energy? I throw it. Well, obviously, the faster I throw this golf ball, the more ability it has to change something else. So if I've got a friend over there and I want to really change their head, give them a lump, I got to throw this thing hard. So certainly the speed or velocity with which an object is thrown helps to determine its kinetic energy. And then the other obvious thing would be, how massive is it? So if I take the bowling ball and I throw the bowling ball at somebody, and then I throw the golf ball at somebody else, if I throw them at the same speeds, clearly you don't want to get hit by the bowling ball. So the bowling ball is going to be, or the mass is going to be a contributing factor in terms of how much kinetic energy there is and how fast we throw something. So the kinetic energy for an object is given by 1/2 times m times v squared. Now, kinetic energy is energy of position. And we've got two forms of potential energy. One of them is gravitational potential energy. In other words, how does something's position affect its ability to damage this bucket? Well, if I have the bowling ball has an ability to damage the bucket. But where would I have to hold the bowling ball in order for it to damage the bucket? Well, obviously, to give it the potential to damage the bucket, I have to hold it above the bucket. Well, how much potential does this thing have to damage the bucket will be an indicator of what its gravitational potential energy is. So what's going to change this bowling ball's ability to damage the bucket? Well, clearly, the higher I get it, the further I get it away from the bucket, the more ability to damage the bucket the bowling ball has. If I'm only using this wiffle ball, then it doesn't have the same ability to damage the bucket that the bowling ball does, simply because it's not as heavy. So weight / mass and height are two things that dictate how much gravitational potential energy something has. So PE sub G, or often U sub G, so U as a symbol for potential energy is often used. That's going to be equal to M times G times H, where H is the height above a particular object. So if I put something above a particular object, then it has the ability to change that object. The second type of potential energy is called elastic potential energy. So really, our mechanical energy, if mechanical energy, M sub E, is the sum total of kinetic energy plus potential energy, and this potential energy is broken down into two types for us, right? Certainly there's chemical potential energy, but for us, mechanical energy deals with gravitational potential energy plus elastic potential energy. So the sum total of kinetic plus potential, or kinetic plus gravitational potential plus elastic potential, gives us our mechanical energy. Elastic potential energies based on position relative to a stretched out object. So here's this rubber band. There's really no energy stored in the rubber band until I stretch the rubber band out. The more I stretch it, the more elastic potential energy ends up in the rubber band. If I take a spring, the more I stretch it or compress it, depending on the nature of the spring, the more elastic potential energy there will be in the rubber band. So clearly, if you want to hurt somebody, one of your friends that you're messing around with, I don't advocate for it, but if you do, when you stretch this rubber band out, the more you stretch, the harder it's going to hurt somebody when they get hit. Again, not advocating for it. If I stretch this thing out, more and more and more, I get more elastic potential energy. What else is going to determine how much elastic potential energy? Well, what type of thing am I stretching? And we've talked about the idea of what dictates the type of thing that I am stretching, and that's the idea of the elastic constant. So if I'm stretching something that's really thick, it's going to take more effort for me to stretch it, which means I end up putting more energy into there, which means the rubber band is going to store more energy. And we're going to talk about all those relationships here coming up. But for now, we want to make sure we understand that the determining factors for elastic potential energy are the elastic constant K and how much stretch or compression there is. And then finally, our last term for today is the idea of power. Well, actually, let's back up here, okay? Our unit for energy is the joule, just like our unit for work. And that's a little preview for us, knowing that the idea of work and the idea of energy have the same unit can tell us that there's going to be a relationship between the two. And that's what we're going to do in the ensuing days here. Now, finally, power is the rate that work is done or the rate that energy is transferred. Again, this sentence is an indicator here that work and energy are related. Now, we're used to 60-watt light bulbs. That's our unit of power, because a light bulb transfers electrical energy into heat and light energy. Power is the rate at which we do that. In other words, look at, if I have to stand up on this chair, then I have to do work to get up here. Well, if I do it really slowly, I'm not using that much power. But if instead I go super quick and try to give myself a workout, then I'm using more power, or developing more power is oftentimes the term that you use for that. So power is the rate that work is done. Anytime we have a rate, we put that over T. We can also say that it's the amount of change in energy per time. Now, our unit for work and energy is the joule, and our unit for time is the second. So a watt is a joule per second. W is a joule per second. Those are our basic terms here that we're going to use in our work, power, and energy unit. Make sure you watch this as many times as you need. You have to understand what those words are. We can't teach higher level concepts without a basic understanding of what those terms are. So use this video, make sure we understand these terms so that when the concepts that intertwine all these things come up, we'll be ready to go.